Howdy. I wanted to go over the trapezoidal rule problem, especially giving attention to the error bound, which was troubling for many. What we have is the integral from -1 to 1 of e to the negative x squared dx. This integral, by the way, shows up in computations of the normal error distribution in statistics. And the directions of the problem tell you to estimate this integral with 4 trapezoids. And so we begin by computing our delta x, b minus a over n. So that we're going to start at -1 and go up in intervals of 0.5. Just like so. Now we need a graph, and so we're going to go to our graphing calculator here. Still got some stuff left over from previous computations, so clear all that out. And we're going to let y equal e to the negative x squared. Just like so. And we're going to set our window size to be -1 to 1, and for the x's, and for the y's, well, not entirely sure what the graph should look like, so -5 to 5 should be safe. I'll give that a shot. And when I graph it, lo and behold, I get a graph just like this. Come back over here and sketch it. So what we're looking at is estimating the area here with 4 trapezoids. And just looking at it, it looks to me like those 4 trapezoids are going to do a pretty good job of estimating. You didn't have to draw them. I just am for clarity. But now, how am I going to find the various function values? Because the integral estimate is going to be b minus a over 2n times 1 times the function at -1 plus 2 times the function at all the inner points plus 1 times the function at 1. And the b minus a over 2n is easy enough. But what about these function values right here? Well, some of you struggled with those function values when you computed them. Let me show you the easiest way to get them accurately. If I go back to the graph here and I hit trace, I can now evaluate the function at the selected x values simply by tracing at those points. So f of -1 is 0.3679. And f of -0.5, my ink got in the way. There we go, is equal to 0.7788. And continuing in that way, I find that f of 0 is 1, and f of 1/2 is 0.7788. Use parentheses so that I don't get those confused with decimal points. And f of 1 is 0.3679. Now, how to evaluate this expression? Well, I just punch it directly into the calculator. If we quit out of our graph, then we can do directly 2/8 times quantity 0.3679 plus 2 times 0.7788 plus 2 times 1 plus 2 times 0.7788 plus 0.3679. And hit enter, and we get the estimate for our integral, which is 1.4628. Just like that. How about the actual value of the integral? The third part asks us to do, or the second part asks us to compute that. And so I'm going to go back to my calculator and let the calculator handle that with second calc and integrate. And it's going to ask me for a lower limit, which I give as -1, and an upper limit, which I give as +1, and it thinks for a second. And it tells us that the value of the integral is 1.4936. So we did pretty well with 4 trapezoids here. How well did we actually do? Well, the third part asks us to compute the actual error, which is going to be the size of the difference between the value we got and the value that we should have gotten. So if I come back to my calculator, quit from there, the result of the integration is stored in the answer. So I can actually do 1.4628 minus the answer, and it will compute for me. Now I need to throw away the negative sign here, so I have 0.0308 as my actual error. Now in the fourth part, I asked you to compute the error bound and verify that the trapezoidal approximation did in fact satisfy the error bound. Some of you reported back to me that it didn't, which was a sign of a problem, because mathematically the error will always satisfy the error bound. That's the point of the error bound, is to tell us that the error will be no worse than. So, the b minus a is simple enough, 1 minus -1, and the n is simple enough. What about the max of f double prime? To get the max of f double prime, I'm going to need to compute f double prime. If f of x is my integrand, e to the negative x squared, then f prime is negative 2x e to the negative x squared. And f double prime, let's see, first times the derivative of the second, plus the second times the derivative of the first. And when I simplify all of that, factoring out an e to the negative x squared, I get e to the negative x squared times 4x squared minus 2. Well, okay, so how does that help me? How am I going to find the maximum of the absolute value of this expression? I'm going to let the calculator handle it. I'm going to go back to y equals and let my y2 equal the absolute value of the e to the negative x squared times 4x squared minus 2. And when I graph that, then my graph clearly shows that this expression has a maximum at x equals 0. So I trace along the red curve, and I go to x equals 0, and get a maximum value of y equals 2. So that the max of the absolute value of f double prime is 2 on the interval -1 to 1. And I come back and I plug in 2 for that max, and I can now simplify this whole thing as 2 cubed times 2 all over 12 times 4 squared. And I can be fancy with it. In fact, I think I will, because 2 cubed times 2 is equal to 2 to the 4th. And 4 squared is 2 to the 4th also, so those cancel, and I get 1/12 as my error bound. In decimal form, 1/12 is 0.0833, and so clearly the error satisfies the error bound, and I can express that just like this, that the error, which is 0.0308, is less than or equal to 0.0833. So the key thing that a lot of people were missing was how to find the maximum of the absolute value of f double prime. And the answer is you compute f double prime by hand and then find the maximum of its absolute value by calculating. Hopefully this was helpful to you.